a cure in sight, offering insights into ocular melanoma. Proudly presents
When you think of the immune system, you think of that's what makes your finger swell up when you cut it and you get an infection, or when you get laid out with the flu. It's the part of your body that attacks bacterial and viral infections. And the lesser well-known role of the immune system is actually finding and killing.
Hi, everybody. Welcome back to the I Believe podcast. I am joined today by an amazing ocular melanoma patient herself and a researcher, Lucy Innes. And today we're going to be covering immunotherapy, the immune system. Think of this as your beginner's guide to what is immunotherapy and what do you need to understand as a patient or a caregiver if you're considering one of these kinds of therapies as a trial or just a primary treatment. With that, I want to go ahead and just bring Lucy in and have her explain and tell us her journey with ocular melanoma.
Thank you so much for having me on. So as you said, I'm Lucy Innes. I was diagnosed with uveal melanoma or ocular melanoma in October of 2022. So pretty recently, and I was in the first year of my PhD when I was diagnosed. I started having all sorts of visual symptoms, and I went to the doctor. I saw Dr. Brian Marr, and he told me he thought it might be uveal melanoma or ocular melanoma. And at first, obviously, I didn't want to think about it. I didn't want to research it. I was obviously really stressed out. But as time went on, I found that it was kind of all I could read about and all I could think about and all I could talk about. And since sort of the job of a PhD student is to read papers, and I was really just reading papers about uveal melanoma, it kind of became the obvious thing for me to do, to research it. And I was treated with plaque brachytherapy in my eye, and so far no sign of metastasis. So that's where I'm at right now. And I do want to say we're going to be talking a bit about the immune system and immunotherapies and what options are. And I want to just give the disclaimer that I'm still in training doing my PhD. And my role here is to help make the biology more accessible to patients, but not to be, a source of medical advice. Your oncologist has a much better understanding of what the best treatment is for you. And really my role here is to help make those conversations a little bit easier.
As we were planning this episode, we really just want you guys, we want to be able to teach patients and caregivers the value of the immune system, but also, continue to give you a basic understanding of what is an immunotherapy and why should you consider it if it's an option, and what is its function. So we talked about this before, Lucy, but when we get into immunotherapy, or before we get into immunotherapy, we really need to have an understanding of just the background of the immune system. So can you just explain what is the immune system, its key functions?
Yeah, totally. So when you think of the immune system, you think of that's what makes your finger swell up when you cut it and you get an infection, or when you get laid out with the flu. It's the part of your body that attacks bacterial and viral infections. And the lesser well-known role of the immune system is actually finding and killing cancerous cells as they form. So what does this look like? And one thing is that the tools that they use to fight bacteria and viruses are actually the same tools that they use to fight cancer cells as they develop. And
That's
so what
interesting.
are these tools, right? I know I had no idea, and I was really surprised when I learned that. So what are those tools? I'm going to try to break this down into simple terms. Before I started studying immunology, I kind of had a vague idea of T-cells. I'd heard of them, it's sort of part of your immune system, but I didn't know really anything other than that they, fight disease. So I'm hoping I can break down the pieces of the immune system and how they fight and how they're able to fight cancer.
So when we're getting into these pieces of the immune system, are we going to kind of cover the key players, of the types of cells that are involved in the immune system?
Yeah, so we'll talk about the types of cells involved in the immune system. So say, for example, a healthy human cell gets attacked and invaded by a virus, like the flu. The first line of defense is the innate immune system. And there's a lot of cells involved there, so I'm not going to get into the nitty-gritty. I'm just going to call it the innate immune system. And these have like a kind of a list of markers to look out for. And these are markers that are on a lot of flu or bacteria cells, and they're also maybe stress markers of the cells trying to say, hey, I think I might be infected, I think something's wrong. And these innate immune system cells will then try to attack and kill those cells. And I like to think of these as sort of maybe the general infantry of an army, attacking an invading army. They don't have a lot of thought process behind it. Like they're really just sort of like, look for this specific thing and just attack, this vague idea of what the enemy looks like. And these are generally pretty effective, and they're pretty effective against flu or like virus and bacterial attacks, and they're also relatively effective against cancer cells, because cancer cells, when they become malignant, they start behaving weird. They start putting out strange surface markers. They start putting out stress markers. And the innate immune system can sort of identify these and kill these cells in the same way they are able to kill virally infected cells. And the next sort of key player in the immune system is called the dendritic cell. And the dendritic cell is, they go to the site where innate immune cells have sort of killed some cancer cells, and they're able to pick up the markers that the cancer cells dropped and take them to the T cells. So I like to imagine this as a sort of messenger in a battle, where the front line of defense, they have sort of a vague idea of what to look for, but the invading cells might find a way to sort of like disguise themselves and look sort of differently. So these messengers are able to write down a really specific idea of like, this is what the enemy looks like. And they take that message and they bring it to the generals. And the generals in this case are the T cells. And these T cells are then able to all get together, make a plan for how do we attack this specific enemy. And that can take a little bit longer, which is why it can take so long to get over the flu, is because it takes a little while to make a good plan. How do we fight this specific army? And so just sort of to recap this, we've got the innate immune system, which is sort of the general infantry, the front line, and they have like a sort of vague outline of, if you see this, kill it, and that never changes. Then you have the dendritic cells, which are the messengers. They will write down a really specific description of this army, and they'll take it to the T cells, which will create a more specific plan to defeat the army. And this works, for viruses, for bacteria, and it also works for cancer cells, so that they'll be able to kill those cells.
So then after we've got the innate cells, they're the general infantry, you said, and then we've got the dendritic cells are the messengers, and the high up on the food chain, so to speak, are the generals. And these generals are the T cells, right? So we're trying to use the T cells, like when the immune system is functioning really, really well, it's because the generals have all the information they need, and they're able to pass it back and forth between the key players in the immune system, everyone down the line.
Exactly. Yeah.
Okay.
And the T cells are really, really strong. So a lot of immunotherapies really exist for are target T cells because they're so effective.
That's such a unique, graphic description to be able to think about, because I love fantasy, so I'm just picturing some of my favorite fantasy battles, like from Lord of the Rings or something like that, and I'm like, oh okay, now this makes a little more sense.
Exactly.
Okay, so these immune cells, we talked a little bit about how they behave, like how each of these players behave. What is it that cancer cells can do to evade these kinds of typical immune system behaviors from the T cells, the dendritic cells, and the innate immune cells?
Yeah, that's a great question. So I'd say there's two main strategies. So as you may have noticed in the first part of this, every way that cells really identify each other and communicate is through surface markers. And it's kind of a vague term, and I'm leaving it vague on purpose because getting into the details would totally I could talk about it forever. So I'm really just going to call them markers. But a lot of the strategies that cancer cells use to evade the immune system is by modulating these markers. So one strategy is by hiding their suspicious markers and hiding their stress markers. Sometimes even just, in the case of uveal melanoma, we might think that there's even not that many suspicious markers in the first place. So when the immune system comes across these cells, it doesn't raise any alarm bells. So I like to think of this sort of like spies. I read this fact recently where one way that people can identify spies is by seeing that they actually cut the brand tags off of all their clothing so that if they get caught, they'll be less easy to track down sort of where they came from. And so I like to think of these sort of evading cancer cells as spies, where they're cutting off their markers so that they're less easy to be identified. And this is a little bit in the weeds here, but one of my favorite immune cells, it's part of the innate immune system, they actually look for cells using this exact loophole. So they look for cells that don't show any markers at all and kill those. And that's the cell that I'm trying to study right now, so I'm particularly fond. Also, natural killer cell is the coolest name ever. The other mechanism which cancer cells might use to evade the immune system is by convincing the immune cells that they're healthy cells. So they might say, hey, I know I look like a stressed cell, but it's actually because I'm damaged and trying to heal. So you should give me resources and nutrients to help grow. You should bring in more blood vessels to help grow. And they can actually pretty effectively get the immune system to stop fighting, to put on the brakes, and sometimes even just help them grow and become, and it can actually support the tumor.
That type of response from a cancer cell might be similar to how a parasite might behave in some ways, where it's feeding off of your resources, from your body, but it's able to do so because it's able to hide from the immune system in such a way that it can, like you said, trick it. It can trick it into just being like, oh, yeah, I understand. You just need a little more time. I'll give you time. And here's all the resources. Here's all the food.
Exactly. It's pretty easy to convince I'm not going to say easy, but our immune system is always on the lookout for, am I attacking healthy cells? Because that can lead to autoimmune disorders, and that's a really big deal. And so there's all sorts of checks and balances to prevent that from happening. And for diseases like multiple sclerosis, that's a case of the T cells are not listening to the checks and balances, and they're attacking healthy tissue. And so that's, it's relatively easy for cancers to use this technique because the immune system is so on high alert to make sure it's not attacking healthy cells.
Okay. And now we're going to go on and we're going to define immunotherapy. So I guess first question, or maybe two questions, is what is the aim of immunotherapy, the main goal, and how does the immunotherapy capitalize on these key players in the immune system, what already exists in your body?
Yeah, so with any cancer therapy, you're really looking for what is different between the cancer cells and healthy cells, and how can you exploit that difference to kill the cancer cells. And that can be as basic as, okay, these cells look different. This patch of skin looks different than this patch of skin, and you can just cut it out. Or say chemotherapy, where the cancer cells metabolize faster than healthy cells. So if you put essentially poison into the patient, those cancer cells will die much faster than the healthy cells. Now, what's cool about immunotherapy is that our immune system already has a lot of tools for identifying cancer cells and healthy cells. and killing those cancer cells. And we're just trying to identify the places where it fails and figure out how to reverse those, how to dial up the immune system's ability to do what it can already do by differentiating healthy cells and cancer cells.
The immunotherapy is created. You basically said that it's with the idea that it's going to use parts of the immune system, or really use the immune system as a whole, in the way that it already exists, but it's going to amplify it. Is that really a good summary?
Yeah.
Okay, so what is something that might be synthetically produced in immunotherapy? Like, there's obviously, we have our naturally occurring immune system, and immunotherapy, especially if it is like an immunotherapy drug that's administered intravenously or orally, it's going to be something that is synthetically made. So what are some of the parts of this immunotherapy that might be synthetically engineered, and why?
Yeah, so it breaks down into sort of, there's immunotherapies that enhance the cells that are already there, whereas there's immunotherapies where you're actually taking cells out, modifying them, and then putting them back in so they'll be better at fighting. And so immune checkpoint inhibitors like Ipi and Nivo are in the first category. So as I mentioned before, one of the strategies that cancer uses to evade the immune system is by saying, hey, I'm healthy, I'm a healthy cell, like, stop attacking, you're attacking healthy tissue. And in the case of T cells, this can lead to what's called T-cell exhaustion, which I think is a little bit of a misnomer because they're not exhausted, they're being told that they're attacking healthy cells. And Ipi and Nivo, our immune checkpoint inhibitors, they actually tell those T cells, ignore that sign, keep attacking, even if you're being told you're attacking healthy cells. So that's a case of just sort of taking something already there and just sort of, tweaking it so that it'll fight a bit better. Whereas there isn't really a case of this for uveal melanoma, but CAR T cells are a big, immunotherapy approach where they actually take the patient's T cells out and they will modify what that T cell is looking for something that they know that the tumor has, like a marker that they know the tumor has, that the immune system just isn't seeing. So they'll take those T cells out, modify them for a specific target, and administer them back to the patient. And then that is how they get those to start attacking the tumor again.
So I have a question. The T cells, like, we talked about kind of the structure of the immune system from the bottom up, so to speak, where we've got those innate cells, then we've got our dendritic messengers, and then we've got the T cells, who are the generals of the immune system. They're the ones kind of making the plan. So if in some of these examples of types of immune therapies, if we are pulling out T cells and teaching them, is it in some way because maybe the dendritic cells just haven't gotten the message yet?
To some degree, we don't really know. We know that some of the T cells are being activated, they're trying to fight the cancer, but that they're failing in some way. And ultimately, like, there's so many possibilities for what it could be. Them being insufficient, like not having it quite enough information, or if the dendritic cells aren't totally sure, like, this might be healthy cell, we're not sure, that can make it so they don't really get as robust of like a no, we need to attack. They might be like, ooh, keep an eye out, but I'm not sure.
Yeah.
So they
like,
can
keep an eye out. This is low-key suspicious, but like not a major threat.
Exactly. So there can be a lot of different reasons why they wouldn't be why they wouldn't really be at their full attacking capacity. And with sort of T-cell directed therapies, you're sort of overriding these checks and balances. So there's a lot of checks and balances on T-cells, and by overriding all those checks and balances, they're able to just, attack and attack and attack. And that is what sort of leads to a lot of the side effects that come with T-cell therapies. It's pretty hard on patients, and there's a lot of, cytokine storms and things like that. And it's sort of because we're overriding a lot of those checks and balances. And it's also probably why they're so effective.
Okay. So let's talk a little bit more about the whole body immune system therapies. So we've got a couple of kind of theories out there in the immunotherapy world of dendritic cell vaccines, using a virus, I think the dendritic cell vaccine is the main kind of vaccine, the cancer vaccine. So just kind of on a basic level, like how would these theoretically work, or how do they work in, the times that they have been investigated?
Yeah, so what's neat about trying to use points earlier on in the sort of immune system cascade is that if you are able to target some of the upstream a bit, then those checks and balances on T cells are able to remain intact. So in the case of dendritic cell vaccines, remember, these are the cells that take a description of the army and bring it to the T cells, say, attack this guy in particular. So scientists could get the perfect combination of markers and just load that into dendritic cells. And also, in addition to that, make the dendritic cells sure this is the bad guy. They're not going to be iffy. You can be like, no, this is for sure the bad guy. And so then they're able to bring in as strong, induce as strong of a response in T cells as possible. And if you take it a step back even further, a lot of the something I've been seeing a bit more often, which I think is really cool, is sort of virus-related immunotherapies. So the Replimune, where they're using a herpes simplex virus, Aura Biosciences, Trisalis, they're all using some sort of virus or even markers associated with viral infection are being used. And remember how I said that the innate immune system has like a list of look out for this guy? That's sort of the idea there, is that they're taking uveal melanoma markers, combining them with these really, really suspicious virus markers. And that way the innate immune system can say, hey, this is totally bad. And that can set off that whole cascade. And I'm really excited that there's more and more therapies that are, starting to be implemented further up in this immune cascade.
So what it sounds like, just maybe in theory, is that immunotherapy has the potential to perhaps be the most effective if we can essentially start with those innate cells in the cascade, the immune cascade. So part of my question that I was leaning toward earlier was if we, activate the bottom point of the immune system and then it ripples up to the top, is that more effective than it is for us to start at the top of the immune system and then come back down? That was kind of maybe where my brain was trying to go. And so it sounds like the theory, at least behind the dendritic cell vaccines and with the viral kind of virus-like particles that are injected, it sounds like it's perhaps the most effective in theory to start at the bottom of the immune system, or maybe bottom isn't necessarily the right word, but to start with those innate cells and to then have the message passed up properly, with the chain, the normal chain of command, so to speak, as opposed to the other direction. That allows the immune system to maybe be the most effective.
In terms of how effective it is, I'm not sure, but it does seem like it's going to have the least side effects, so you could maybe use a lot more of it. Whereas
that actually is a better way to describe it. That it's the cost to the healthy cells, the cost to the whole body is going to be lower with the things that start at the innate level versus the things that start at the T cell level.
Exactly. So, in the case, T-cell directed therapies are really, really effective, but since you're getting rid of all those checks and balances, it can cause a lot of sort of collateral damage. And, it may be just as effective, but you can administer so much less. A lot of people using Ipi/Nivo have to stop temporarily because they have this huge immune response. And if you're able to, keep all those checks and balances intact so that it's only attacking the cancer cells, there'd be less incidences of having to stop for the patient's safety.
Okay, so I feel like we're getting into kind of more of our next section, which is great. So let's talk a little bit about the role of the immune system specifically in uveal melanoma. And this is, I know, kind of where your your magic is. This is where you've been studying. So can you just give us a little bit of a lowdown on uveal melanoma and the immune system, and perhaps why uveal melanoma cells are able to evade the immune system, sometimes for 15, 20 years in some types of metastatic cases? So I'm going to turn that over to you because I don't know that answer.
Yeah, totally. So I described a couple different mechanisms by which cancer cells can evade the immune system. And it kind of seems like uveal melanoma is the master of this. It's the master at evading the immune system for a number of reasons. When you compare uveal melanoma with skin melanoma, uveal melanoma is a much, I'd say, quieter cancer. It has a lot fewer suspicious markers. It hides a lot of its stress markers, and it's really it's much less, noisy to the immune system. It's also, I don't know how many of you are familiar with how immunosuppressive the eye is, but inside of the eye, the eye is so delicate that if any immune response is sort of engaged in the eye, it's really likely just to lead to blindness. So the eye is constantly telling the immune system, stay out. If you're in, I want you to go completely kind of dormant, like you're not attacking anything. And we kind of think that when a uveal melanoma cell leaves the eye, it's able to take that immunosuppressive power with it. So that when immune cells come into the tumor, they're sort of given all the same signals of don't attack here, this is healthy cells, these are not the droids you're looking for. And so it seems like it's really good at kind of every strategy to evade the immune system.
Oh my goodness, that's a good descriptor. These are not the droids you are looking for.
Exactly.
Okay, but we want to use the force in the other direction.
Mm-hmm.
So, all right. So let's talk then about some of the FDA-approved treatments that we currently have for uveal melanoma. What are some of the things that you have seen used? And I think we talked briefly about checkpoint inhibitors, and we've talked a little about Ipi-Nivo, but let's talk about Ipi-Nivo, and let's talk about the Kimmtrak-Tebi kind of concept, and anything else that is relevant.
Yeah. So in terms of so these are all T-cell therapies, and the thing that's kind of interesting is that these treatments tend to work a lot better, especially immune checkpoint inhibitors seem to be working a lot better against skin melanoma than they do against uveal melanoma. And this might be because if you remember what I was describing about with immune checkpoint inhibitors, they make it so that when T cells are told to stop, they'll ignore that signal and keep attacking. But if they're never told to attack in the first place because they're suppressed, they don't even see any markers to attack, this isn't going to, they're not even being told to stop, so something that tells them to ignore that isn't really going to do anything because they're not attacking in the first place. That being said, there's definitely more to the story because we do see T cells that are in this sort of suppressed mode that are being told to attack and stopping. So there's definitely some in there, but we haven't quite figured out the puzzle piece of why the immune checkpoint inhibitors aren't doing that much to get them to attack.
It's almost like something sounds like it's getting lost, like some part of the message is getting lost between, I don't know, maybe there's some in-between layer between the dendritic cells and the T cells, and that they're just playing telephone and somebody's misinterpreting what somebody said.
Exactly. And I think it comes from we have a pretty amazing idea of what are all the different immune checkpoints, but we also don't know everything. And there's definitely some research recently that's discovered LAG3 as maybe a potential target to use to target immune checkpoint therapies at. And we wouldn't have known to try that therapy if we hadn't sort of seen that LAG3 was being expressed in the tumors. And it just that just goes to show that it's not just like one marker, you just reverse that one marker, you're good to go. It's really, really complex. There's a lot of different markers. And I'm sure we'll learn more about the story as time goes on.
So we talked briefly about like Ipi/Nivo kind of over the course of this, and we've had somebody just kind of talk a little bit about in their question, they asked about the Ipi/Nivo side effects, and is there, when you're under an immune therapy or when you're being administered immune therapy or immunotherapy, are there things that can be done to mitigate side effects? Like, have you been able to see any of that in your research that maybe allows for the immune system to keep those checks and balances and to also mitigate the cost to the rest of the body with those side effects?
That's a great question, and I think it's a bit outside of my expertise. Like, I think that's a lot more of what the clinicians work with day to day, and I think from my research is more looking at how can we design therapies that keep those checks and balances intact. So I'm not necessarily the best person to ask for that.
No, that's okay. I wanted to just kind of pose the question just so that we could get that out there.
No,
so it sounds like for this person, Daniela, who's listening live, thank you for being here live and listening. But it does sound like that would be a question to pose to the clinician side. So talking to your oncology team or your patient's oncology team. I think you mentioned it was your mother with ocular melanoma. So let's talk a little about like the way that KIMMTRAK works. This is kind of the newer FDA approved treatment. It was recently approved in the last couple of years. And the people that it's been effective for are specific to the HLA-O201 positivity in that expression, which is a blood biochemistry marker that they can have checked. I think that the way that I've heard it explained is that your HLA typing is almost like the blood type of your organs. At like a super basic level, like you have to have HLA type and blood type match in order for you to get like an organ transplant. So anyway, the HLA-O201 positivity, what is the significance of that you've seen like in KIMMTRAK and Tebi?
Yeah, that's a really good explanation for what the HLA, description of HLA. So KIMMTRAK or tebentafusp is what's called a bispecific T-cell engager. So bispecific means that it has sort of two sticky points. One that sticks to T-cells and the other that sticks to a specific marker that the doctors decide. And so this is similar to CAR T-cells, where you're making T-cells look for a specific marker that they decide, doctors decide beforehand. But this works by you administer this to patients and it sticks to T-cells, and then it also sticks to the marker on the cancer cells you're looking for and forces them to interact. And just this forcing them to interact is what is able to cause T-cells to start attacking those cells. This is a really, really cool new piece of technology because and I actually think that uveal melanoma is the first case of a bispecific T-cell engager being approved, or maybe the first time in solid tumors that one is being approved. And it's really exciting because since this has been approved, there's been a lot more interest in uveal melanoma, a lot more clinical trials, and I think it's really raised a lot of interest for research in uveal melanoma.
Yeah, that's so exciting. So you mentioned that it's possibly the first immunotherapy of its kind that's been approved for solid tumors. So as far as the way that it works, I think that what I've heard around immunotherapy, like for example Ipi/Nivo, is that Ipi/Nivo is perhaps less effective, at least in a clinical setting, against metastases in the liver versus if you have, say, bone metastases or lung metastases, something on the skin, like kind of some of those lesser common locations to have metastases, that the Ipi/Nivo can be more effective in those specific cases versus the liver itself. So is there maybe an explanation for why that might be in the case of the different types of immunotherapy? Does it have anything to do with the checkpoint inhibitor aspect, or?
Definitely, like, I mean, there can be a million explanations why. So the liver is highly, highly immunosuppressive. And so so potentially the way that the bispecific works, where it's forcing those interactions, it might make it so that kind of overrides the immunosuppressive environment of the liver. But ultimately, there's a lot of different things that it could be, especially in the liver. Like, the liver is such a complicated organ, and we're still sort of learning so much about why it's so good at suppressing the immune response.
No, that's such a good point. And honestly, as far as key things that I've learned today, I had no idea that the eye was so immunosuppressive, which, I mean, if you think about, in theory, for people who go through their diagnosis journey and they have a massive tumor that's found in their eye, right? Like, if the immune system is so good at doing what it does, maybe on a whole body level, but then in the eye, it is suppressed intentionally so that you don't just go blind from every little speck of dust that ends up in your eye, then it makes sense that a tumor could go undetected for as long as it does. And it doesn't necessarily, I don't know, it doesn't make it any better that you have a massive tumor found when you're a patient with a massive tumor, but it does at least offer an explanation for why did it go so long. It's because the eye is so good at making sure that you don't go blind unless it's absolutely necessary.
Exactly. I know, it always makes me wonder, like, why isn't there more cases of cancer in the eye if it's so immunosuppressed? I don't know. That's something that I've kind of wondered, and I don't know the answer to.
Yeah, no, that's a good question. So speaking of questions, as we're wrapping up, we do have a really good question that I feel like rounds out our discussion and just kind of ends this on a really good note for us. But this question is from John, and he says, what do you see as the most promising area and the biggest need for research, like in your experience thus far, as you've been more specifically studying uveal melanoma and the immune system there?
So this is something that I noticed when I entered the field, is a lot of the research papers that I was just trying to read as much of the literature as possible. And the majority of the literature is describing patient samples. So looking at what exists already, using more and more advanced technology to explore patient samples. And I think that comes from the fact that a lot of the uveal melanoma researchers are clinicians. And the thing that I'm trying to do from more of an academia side is trying to do more functional assays and looking at, if we modulate this gene, how does that change how it interacts with the immune system? If we alter the conditions, and doing more experimental approaches, from hypotheses generated from that sort of descriptive data, looking at patient samples. So I think that's something that I'm really trying to do, is sort of take the academia approach and doing more experimental research as opposed to descriptive, and sort of quantifying patient samples.
Oh, I think that's such a good point. And we kind of already alluded to this, but I did want to just revisit this. Why wasn't FDA approval of the Kimmtrak therapy and the tebentafusp? Why was that important to the future research for immunotherapy in uveal melanoma? Let's just kind of revisit that one more time to make sure that we hone that, kind of drill that home.
Yeah, I mean, I think in a way it's kind of advertising for uveal melanoma. Drug companies can only survive if they get drugs approved. And so when there's a big success, especially sort of a first of its kind class of cancer treatment being approved in uveal melanoma, it alerts a lot of other drug companies to say, hey, this is a really good place to study. This is a really good model to try out our new drug. And so it's going to lead to a lot more. It already has led to a lot more trials being conducted in uveal melanoma, and I'm really excited to see what is going to come next.
Oh, I agree. It's super exciting. So as far as where the research for uveal melanoma is going, it sounds like, at least from what you're seeing on your end, there's a lot more research being done into what can happen, right? Instead of just what is happening and what do we see in a clinical setting with a patient, we're trying to then take it a step further back and to say, okay, well, if we think this happens, what happens if we apply that, hypothesis in an experimental setting in a lab. And then we've also got, just kind of in summary, we've got a deeper understanding. The longer we go in science and technology and cancer research, we have a deeper understanding of the immune system, of how it works and the types of therapies that can be introduced at various different points of the immune system. So all of that, it seems like, is coming together in a positive way for uveal melanoma, as far as just the trajectory of where this could go in the future. So is there anything you want to, just kind of as we end, is there anything you want to just explain about where you see maybe the future of research going, maybe in like the next 2 to 5 years?
Yeah, so I don't know if anybody's been following Hank Green on YouTube. His journey with Hodgkin's lymphoma, but he talked a lot about how when he got chemotherapy, which is really effective for Hodgkin's lymphoma, and he got a combination of chemotherapies called ABVD. And that was essentially where there's a bunch of different chemotherapies that all work to some degree, but work much better when they are all combined. They're able to use less of each drug to get the same effect, and they work synergistically. I'm really hoping that as the field of immunology and immunotherapy grows, we'll see the same thing, where it's not just focus on T cells, just focus on dendritic cells, just focus on this, where we're able to combine aspects, the most effective aspects from every single, part, and combine them together to have a really whole immune system effect and optimize every part to have the biggest effect with the fewest side effects.
I think that's so exciting. And I love how you explained it in a way where it's this hope for something that maybe is not just an isolated therapy, that it is working in harmony with something else. And that maybe the answer doesn't lie in one type of therapy or one specific way to administer the therapy. Maybe it lies in this idea that there's a combination, and that everybody's combination, every cancer's combination that is effective might look different. And to just be willing to explore that. I love that. Okay. Well, I think that we've gotten our questions answered that we've had come in. Wonderful. Pretty well covered. If anybody, as you're listening to this recording, if you're listening to this and you have questions, please feel free to reach out to us. You can send us a message by email or on social media at contact@acureInsight.org. And we are happy to do our best to send those questions on to Lucy or to someone else who might be able to help answer questions. But Lucy, thank you so much for being here. Thank you for the research that you are doing and just the direction that you've chosen to take your studies. And thank you for being a guest on the I Believe podcast.
Thank you so much. I've been listening to your podcast a bit lately, and I really appreciate how much you've been doing for this community.
Well, thank you. It is my pleasure. And guys, everyone who's listening, Omi Army, we will see you next time.